All right, let's talk about artificial intelligence. You hear about it everywhere, right? Today, we're going to cut through all the hype and the sci-fi stuff and get right down to the real core ideas that are actually powering the AI revolution. So let's jump in. But before we can even get to artificial intelligence, we have to back up and ask a much, much tougher question. What even is intelligence? Seriously, think about it. Is it just knowing a bunch of facts? Is it about solving tricky puzzles? Maybe it's being creative? This one question, well, it's the bedrock of the entire field. So if you're going to build an intelligent machine, you need some kind of blueprint, right? A goal. And what's fascinating is that there isn't just one. Nope. Researchers have basically come at this from four totally different directions, each with its own idea of what success even looks like. In this grid right here, this is basically the map for the entire field of AI. It all boils down to two big questions. First, are we trying to make something that's human-like with all its quirks, or something that's perfectly logically rational? And second, do we care about what's happening inside its head, the thinking, or just what it does on the outside, the acting? So you end up with these four camps. You've got folks trying to model the human brain exactly, that's thinking humanly. Then you've got others who don't care how it thinks, as long as it acts like a person. We'll get to that. On the other side, you have the pure logic crowd, the thinking rationally approach. And finally, the acting rationally group, which is all about creating an agent that just makes the best possible move every single time to get what it wants. This whole push and pull between being human and being perfectly rational, that's a huge theme in AI. Okay, so that acting humanly box, this is where the famous Turing test comes in. It's a classic. The test doesn't care one bit if the machine thinks like you or me. It has one simple, brilliant question. Can it fool you? Can it hold a conversation so convincingly that you have no idea you're talking to a machine? Alan Turing's whole point was if it can pass for human, then for all intents and purposes, it is intelligent. It's not about what's inside, it's all about the performance. All right, so let's say we've picked a goal for our AI. Now comes the next huge problem. How do we get knowledge about the world into the machine? I mean, the real world is messy, it's chaotic, it's complicated. How on earth do you translate all of that into a clean, structured language that a computer can actually understand and work with? Well, it's basically a four-step journey of simplification. You start with the actual messy external world. From there, you have to pull out the important stuff, create a conceptual model. So for a university, you don't care about the color of the walls. You care about students, courses, professors. Then you have to define the rules that connects them. That's the formal schema. Things like a student enrolls in a course. And once you have all that, finally, you have a clean, organized knowledge base that the machine can actually use to think. And that bridge, the thing that connects our human ideas to the machine's knowledge, that's called a formalism. Honestly, you can just think of it as the grammar and vocabulary for the AI. It's the super strict set of rules that lets us take a fuzzy concept and pin it down with absolute, crystal clear precision so the computer doesn't get confused. Okay, but everything we've talked about so far is about us, humans, carefully building and programming all that knowledge into the system. But let's be real. The magic of modern AI, the thing that's really changing the game, is its ability to learn for itself. So the big question is, how does a machine stop being just a static database and start learning from the world on its own? Turns out there are two main ways this happens. First, you have supervised learning. This is kind of like giving the AI a textbook with all the answers in the back. You feed it tons of data that's already labeled. This is a picture of a cat. This is a picture of a dog. And eventually, it learns to see the patterns. Then you have unsupervised learning. This is totally different. It's like dropping the AI into a massive library with zero instructions and telling it to figure things out. You just dump a whole bunch of unlabeled data on it, and its job is to find the hidden patterns and structures, all by itself. But there's another way for machines to learn, and this quote really points us in the right direction. It's an incredibly powerful method that's inspired not by textbooks or libraries, but by the most powerful problem solver we know, nature itself. I'm talking about evolution. So, what if, instead of trying to engineer one perfect solution, we just didn't? What if we created a whole population of pretty mediocre solutions? Then we make them compete. The ones that do a little bit better get selected to create the next generation. We throw in some random mutations to add new ideas to the mix, and we just let this process run. Over thousands of generations, just like in the real world, the solutions evolve and get better and better, all on their own. Now, this is a really profound shift in thinking, right? We stop trying to be the genius who designs the perfect answer.
Instead, we become the designer of a process, an evolutionary process that finds the answer for us. It's an absolutely incredible way to tackle problems that are just way too complicated for a single human brain to wrap its head around.
Okay, so we've got an AI that can know stuff and learn new stuff, but that's all happening inside the computer, right? It's all internal. So how does it actually do anything in the real world? What's the bridge from thinking to doing? The idea that bridges that gap is something called an intelligent agent. Now, this could be anything from a software bot on the internet to a physical robot. The key idea is super simple. It has sensors to perceive the world around it, like a camera or a microphone, and it has actuators to act on the world, like a robot arm or the motor in a self-driving car. It senses, it thinks, and then it acts to try and achieve its goals. And check out this brilliant example of that in action: ant colony optimization. Let's say you have a super hard problem, like finding the shortest possible route to visit a bunch of cities. What you can do is create a bunch of simple digital ants. Each ant is a really dumb agent. They just wander around randomly at first, and as they go, they leave behind a trail of digital pheromones. Now here's the clever part. The ants on the shorter paths will finish their trip faster and make more trips, so those paths get more pheromones more quickly. Other ants are attracted to the stronger trails, and pretty soon the whole colony naturally converges on the best, most optimal route. This incredible phenomenon has a name. It's called swarm intelligence. And just think about that for a second. No single ant has any clue what the best route is. There's no boss ant giving out orders. The brilliant solution just emerges from a bunch of simple little agents following a few simple rules. It's a powerful idea, right? That you can get massive intelligence without needing one single giant brain. Okay, for our last piece of the puzzle, let's pop the hood and look at the hardware. Because all of these amazing ideas, deep learning, evolutionary algorithms, swarm intelligence, they are hungry. They need a staggering amount of computing power. So what's the engine that's actually making all of this possible today? The secret, it turns out, was a big shift in hardware. See, a normal computer chip, a CPU, is like a master watchmaker. It has a few incredibly powerful cores that are brilliant at doing one complicated thing after another really, really fast. But a GPU, the graphics card that was first built for video games, it's totally different. A GPU is like an army of thousands of apprentices. None of them are geniuses, but they can all do a simple task, and this is the key, they can all do it at the exact same time. And that ability to do things in parallel at the same time is what changed everything for AI. Training a big AI model means doing millions and millions of pretty simple calculations. A CPU, that master watchmaker, would have to do them one by one. It would take forever. But a GPU, the army of apprentices, can chew through thousands of them at once. This massive parallelism, that is the engine that unlocked the whole modern era of AI. Which kind of brings us full circle, doesn't it? When you look back, so many of the most powerful ideas we've talked about, from algorithms that evolve to the intelligence of a swarm, they're all inspired by nature. And as we build these artificial systems to be more and more powerful, it really makes you stop and wonder, what other secrets is the natural world just waiting to teach us? What's the next big idea we're going to borrow from life itself?